Hello everyone. In previous series, we have seen finite element the analysis of a beam, but because of some reason, I cannot provide visualization model because um, due to some issue, my file was corrupted and I was not able to recover the file. So in this series, we will perform a finite element analysis of a slab, and in this I will show you the visualization model also. So first of all, we need to save the model. Open the model by using uh, open a new model database with extended explicit model, and just Control plus S to save the model. Name it as anything you want. Click on continue. Now for cross section, I just take a slab of 1 meter into 1 meter, and depth will be let's say 100 mm or 150 mm. We can say. Okay, so let's create the cross section first for better understanding. For example, let's create a rectangle first for beam, slab. Here, okay, let's create a rectangle first. Draw. Okay, this is cross section of our slab, and this will be, let's take 1 meter. Let's take this is 1 meter, and assume this depth is 150 mm. So we want bars here like this. Okay, so what we can do, just take this bar as 8 mm dia bar, or you can say 10 mm. Let's take 8 mm bar, and the spacing, let's take 100 mm center to center. This is all just assumption. Okay, this is not as per any code or design. I am assuming all this. And for distribution reinforcement, let's take this bar also 8 mm at the rate 100 mm center to center. Now again, the same thing, we want to find the distance of this bar, just first bar, which will be here. For example, if I take this as a coordinate, then here we want this distance, and also this bar will be look like this. Okay, almost. So here we also want the distance. So let's draw it properly. This bar will continue like this, okay, in this direction. I have not created till the end, but for assume that this bar is continuous till here. So let's take effective depth be effective cover be 25 mm. If we take effective cover be 25 mm, then this distance will be 25. Okay, I don't know what is happening. Okay, this distance will be 25, and also the horizontal distance will also be 25 mm. And similarly, if we take this as 8 mm, then up to this point we need to find. So this distance will be just 4, that is this distance, plus 4 mm, that is this distance. So what we can do, this distance will be 25 plus 8, that is 33 mm. Okay, so first we will create slab, and approximate size will be 1000. That will be all the solid homogeneous. Okay, now create a rectangle, 0, 0, and for in x direction our width is 1000 mm and depth is 150 mm. Done. And our depth is again 1000 mm. So here the slab is created. Now again create a part, name it as bar, which will be wire, and the length will be 1000. Click on continue. Again minus 500, 0 to 500, 0, enter. Now we need to create a support, or in this I will show you the punching shear failure. Okay, so let's see. Now go to property, and in previous lecture we already see how to create the material properties. So I just import these properties, and let's check the material property. It is 30 M30. Okay, and this is general mechanical last. Let's make it FE 500 or FE 550. So at 550, 0, click OK. Now create section. First slab M30. Okay, assign section, done. Slab. Okay, create another section, bar 8, beam truss element. Okay, and material will be FE. Cross section area will be 50.26. Click OK. Go to bar, just assign the section. Okay, now in assembly, first of all translate this by 25 in x direction, 25 in y direction, 500 in z direction. Okay, we need to check the xyz coordinate. So here just delete this, or okay, now in z direction we need to move 25 mm, in y direction we need to move 25 mm, and in x direction we need to move 500 mm. You can see in x direction we need to move 500 mm. So 500, 25, 25, press enter, click on OK. Now again translate, create instance, bar, continue. Now rotate this bar. Okay, in this direction we need a bar, done. Now translate this bar, done. In this case, in x and y direction, press enter. Now again in x direction we need 25 mm. Similarly in y direction we need 33 mm, and in z direction we need 500 mm. Press OK. Now simply just remove the slab part and Okay, remove slab part, go to view, assembly display option, render beam profile. Okay, so they are perfectly placed, no problem here. Now create a linear instance of these bars. First this bar, I want bar in this direction, select direction, distance will be 100, flip the direction, and here we can see we need to adjust the distance. Okay, so what we can do, 1000 minus 25 minus 25, that is 950 mm. Okay, 25 from here and 25 from here. If we need 10 bars between this slab, then just divide it by 10, that is 95 mm. If you assume the distance, then it will be fine. Click on OK. Similarly, create linear pattern of this slab, this bar. Click on done. Again, just make it 1, and here put 95. Flip the direct, select the direction, that is this. Flip the direction, click OK. Now go to step module, and before coming to step module, we need our beam to be slab to be fixed. Okay, we need our slab to be fixed. So how can we fix our slab? Just go to part module. If we just fixed at this center, these edges, if we fix our slab at these edges, for example like this, create boundary condition. If we select this edge, then there may be some, you can say that there may be some local failure here. Okay, local failure of concrete at this edge. So what we can do, we just create support until this point. Okay, let me show you in part model. Just go to edit feature, select the face, go to partition face, select this and select this edge. Now just select offset, select everything, click on done, and select, let's take 30 mm. Okay, done. Now this part, okay, you can see this part will be fixed also, along with this side faces, some part of top faces, that is this part will also be fixed, so to avoid any local failure. So similarly in bottom, we will apply again 30, press enter. Now we need to flip. Okay, done. Now again, one thing we can do, to apply the load here, you can do two things. That is, first create a support part and place at the center and apply the load on support part. And the other thing what we can do, just partition the face. Okay, also partition this face also and apply the load on that face. So this is a new thing. To apply a support, we already saw in beam. Okay, now in this, let's try a new thing. So again, go to partition face sketch, select this, click on done, select any edge. Now let's calculate the distance. Okay, in this, for example, draw, this is our slab and this is fixed part. Okay, So this is our slab, and also one thing we also want it is center. Let me understand. So you can see this shaded part is also fixed. Okay, this part is also fixed, this whole part. And we know this distance is 1000 mm and this distance is 30 mm. So this distance will be 1000 minus 30 minus 30 from left and right side. Okay, so it will be 940 mm. Okay, we need to find this distance. Okay, we need to find this distance. So what we can do, let's the total length of this be 100 mm. 100 mm. Okay, so this will be 50 mm and this will be 50 mm. So and this distance is 940 by 2, that equals to 470 mm. 470. Okay, so that this distance will be 470 minus 50 mm, that is 420 mm. So we need offset of 420 mm. So again go to offset, select these 4 sides, click on done, and 420 mm we have calculated the offset 420 mm. Press enter and you can see here our this face is also partition. Click on done. Now we will apply the load on this face. Now go to step module or assembly module, go to tools, create set, create, name it as load, continue. Now here select this face, again this face, this face, this face. Okay, all 4 side faces are selected and top and bottom faces also selected. So just click on done. Now go to step, before step go to enter. Okay, in step just first create a step which will be dynamic explicit. Click on continue and make it 0.1 mm. Okay, now go to interaction first. In interaction here click on create reference point. Now to create reference point, this distance is 0,0, this distance is 500 and this distance is middle of this is 500. So we need reference point here. So what we can write, 500. Okay, let's check coordinates. So we need to enter only z and x coordinate. So x and y will be 0 and z will be 500. Press enter here. So at the bottom mid of at the bottom face, mid of the bottom face, we can say that at the mid of the bottom face we got a reference point, so we can get mid span deflection. Now go to step, before step you can create set also, create. Now name it as deflection, select reference point, click on done. Go to step and here select desired things. Okay, remove VA in forces. Okay, only this, remove contact, Here damage in tensile, compression, shear, and for strengths just remove this one, and also this one, and for stress remove this one. Click on OK. Go to history output, create history output named as deflection. For deflection, go to select set deflection and select U2. Create, load, continue, set, select load, and here RF2. Click on OK. Now go to interaction. Okay, first create a coupling. We need to attach this reference point to the surface. Select this reference point, click on done, select surface, click on done, and just click OK. Now go to, okay, we need to embed the bars in slab. So go to again constraint, embedded region, select everything, skip reference point. Okay, I will allow the 5 mm tolerance. If any of bar are merging out of the slab, then it will ignore. Okay, it will be ignored by the ABAQUS. So go to load. Now again add the beam, slab. Here first create load in step 1, that is pressure load, and select this surface. Total force of, let's say, 1500 kilonewton. 1 2 3 more. Go to here, I will select tabular or smooth step 0 0 0.11. okay, amplitude 1. Okay, now create boundary condition in initial step. Symmetry, we have already created set named as load. Okay, we fixed that ends. You can now see that up to this distance, the top surface and bottom surface are fixed. So to avoid any local failure, you can see the bars after the bars are embedded in this support to avoid any local failure. Similar thing we can do in this four faces also. So go to again part and partition this face, select this face, select, okay, all 4 faces we have to select. Done. Okay, let's do one by one only. Okay, we don't need to do this because this whole face will be fixed. So I think we cannot edit this right now. I think there is no feature to remove the partition sketch option. Okay, let's see what happened if we have this partition. So go to step again, fill output and history output we have given, interaction we have completed. Now go to load, and for load you can see this face. Okay, now go to part again, create the slab. Here I have done stack. Part 2. Okay, here we have completed all this. Now just go to mesh module and by part. Now you can see there is another one problem, we cannot mesh it directly. You can see the selected regions cannot be meshed automatically. So how to solve this error? So it is asking for create a text shape or manually mesh using the create bottom meshup tool. So here we have assign mesh control and we can use tetrahedral shape and just click on OK. Now you can see the changes color, its color changes. So just go to maximum, I think 20 mm will be okay. Click on OK. Yes, you can see we have easily meshed this thing. Now we need to mesh the bar. Just mesh default. Okay, assign explicit truss element. Similarly in slab, assign explicit 3D stress element, that is tetrahedral. Now here here we cannot use incompatible. I think it is modified quadratic tetrahedron, or if we go to linear, then we have a 4 node linear tetrahedron, and we can use hybrid formation. So I will just suggest explicit 3D stress quadratic modified, or yes, okay, it will be a 10 node element. So here you can also use, okay, only tetrahedric is available for this, so just click on OK. Now submit the job and we will see the visualization in next lecture. Okay.